Good morning, everyone. This is the fourth day of our lectures. So, and today we have it's a double barrel. So we've got 2 hours. But what I'll try to do is, and in those 2 hours, I'm going to cover mainly droplets, evaporating droplets. But I'll be showing you how lubrication theory and how stability analysis can help give us some insights. And then I'll give you an example of how you can incorporate them in practical situations. So there would be 2 lectures today. So one is basically on stability of evaporating droplets, multi-component evaporating droplets. This work is very fresh. We are formulating a paper from it, so it's not yet published. The student has just graduated, so basically it's very fresh out of the oven, you can say. Okay, so one of the things we are looking at, obviously yesterday we looked at is pools, how multi-component liquid pools evaporate, and we saw that there are 2 modes in which they can evaporate. One is an oscillatory mode where you can have different patches, and the other one is a monotonic instability where you can have puddles. Okay, in case of droplets it's a bit more complex. In case of droplets you've got a strong contact line, and the contact line physics there determine the motion of the droplet, determine the consequence of the state of the droplets as well. So this particular example is another experimental example. This is basically a kidney-shaped droplet, which is basically comprised of water and ethanol, and we are having an IR image from the top. So what we'll see is this white region is basically ethanol, and the less white region is water. And you can see that as the water evaporates, as the droplet evaporates, there is actually phase segregation happening. So you've got these 2 components which are actually separating out. It's like in a mini distillation thing. But then most of the segregation happens towards the region of minimum curvature. Okay, so this we have studied very intensively for various configurations, and we found that there is some sort of a preference to contact line. There is some sort of a preference to a contact line where there is minimum curvature. Okay, and also when you look at the image from the top, it's not a very, you begin from a nearly homogeneous liquid, but then you can see this kind of phase segregation patterns happening. So there is a lot of convection, there's a lot of mixing, there's a lot of segregation which is happening. Okay, now there are various issues with it. Now if you have a coolant which has multiple components, and one of the key methods what experimentalists use is PIV. Okay, PIV to understand what is happening within a droplet. The problem with PIV is that they're particles, and particles, they can have their own motion. What we assume is that they will obey the motion of the liquid, but sometimes they don't. But what they can do is, because of particles, they can actually remix the system. Okay, so that is one danger with PIVs, especially with these systems. So we want to really understand these systems pretty well. The other thing you can see is, I've already shown this video, I think, is basically how do I probably, sorry, is escape, is it? Or? Okay, thank you. So basically what we can do here is, if you look at, this is again a glass slide with several droplets, and each one has a different property, and this is determined by the color. So what you can see is that as these droplets evaporate, they can actually chase, they can actually attract each other, they can sometimes repel each other, and so on and so forth. And that is completely because of soluble Marangoni, but at the same time there is also a vapor on top of it which is playing a role in this kind of motion. Okay, now if you look at more recent work, I'm going to play this one. I'm going to show the video. So the thing is, this is a very simple experiment. So this is basically depositing a water ethanol droplet on a copper substrate, and you're looking from the top, and you can quickly see that it spreads. It spreads very quickly. I mean, this is actually a slowed down video. It spreads very quickly, and as it spreads, because ethanol is more volatile and it has less surface tension, it is driven to the contact line. As it's driven to the contact line, because if it's low surface tension, it's going to spread. But as soon as all of the ethanol is evaporated, you've got a water-rich system, which is higher surface tension, so it's going to retract. So you can have this spreading as well as retraction behavior, and we can also get exponents and things like that. Okay, this is a fairly recent one. Here I'm going to tell you more about this video later on anyway. This is where you've got water morpholine droplets which are actually repelling each other because of the presence of vapor around them. Okay, so I'm going to come to that shortly anyway. Okay, so let's just look at a single sessile droplet problem. So the single sessile droplet problem is a very simple one. If you have pure water, you have simple, you've got evaporation as it happens, and you can see that this is a time snapshot. So even after 4 seconds, you still have a bit of a droplet left. But then what you do is same volume, you just have ethanol water mixture. You can see dramatically different dynamics happening. You can see these development of spokes. This is where you are basically in a very early stage. As soon as you deposit, you will see the spokes. So this is basically what we think is more linear. This becomes a non-linear. So the instability here is linear. It grows up to become a non-linear instability here. You can see these patterns. You can actually, some of these spokes as well merge to form bigger waves and things like that. Okay, this is where a lot of merging has happened. And then once all of the ethanol is evaporated, it's going to shrink completely, and you can compare at the same time. You've got a dramatically different kind of a state. Okay, and what we call these spokes is some sort of an octopus. It's like an octopi arrangement, and the idea is if you have any kind of a coolant which has alcohol water mixtures, what is driving this? What is driving the whole thing? Because the moment you have these instabilities, there is a chance that you will, if normally all coolants are not pure, so you will have some particle deposits. They can lead to deposits as well. Okay, which can lead to fouling, or if it's good for printing and all that, you can use that in that way as well. So the question is, how can we identify and actually understand what is the driving instabilities in a binary mixture droplet? So yesterday, what we were doing is, yesterday we were just looking at a pool. So we had a pool. And we had a wall which was at a higher temperature, TW or T, whatever it was, I think TW. And then you've got a pool over here of a thickness HO and length L. Okay, and the length was L. And the key assumption we made was that HO by LO is a shallow water parameter epsilon, which is much, much less than 1. So it's a very thin film. Okay, so over here, we're going to do a very similar approach, but however, you have a droplet here. So if you look at this droplet very carefully, you will see that you've got a very fine droplet. So if you say the apparent contact angle is less than 30 degrees. Okay, so this is a shallow water droplet. So you can see that you're basically into more of a hydrophilic surface. Okay, and then what we're going to do is, so you've got this apparent contact angle, and what we assume is, if you have a volatile mixture, A and B, A being volatile, B also being volatile, there is always a precursor film on which it will sit. There is always a precursor film. It won't be just sitting on its own. Okay, it won't be a completely dry thing. So what we also assume is a precursor film. Okay, so therefore there are two things. So one is, not only precursor film is a mathematical device to reduce the to eliminate the contact line instability, contact line singularity, but actually physically these precursor films are present, especially if you have a volatile system. Okay, now if this is a precursor film, basically the way it works is, you've got this wall, you've got the contact line. The more volatile molecules in the contact line, they form this precursor film. Okay, and this is basically a very nano level film here. Okay, so nano level film here. So one of the assumptions that we can make in this particular film is that this particular precursor film does not take part in any phase change. Okay, the film is so small and it's so thin. It's a nanometric. It's probably some molecular layer, whatever it is. It's so thin that it doesn't really take part in evaporation or condensation. If it would have done, then you would actually form a pool of film. Okay, there would be evaporation of the film, there could be condensation of the film, and all kinds of things like that. Okay, so what we'll do is we make an assumption that there is no evaporation going on, there is no phase change going on in this particular side of the film, in the precursor film. That means that I have to actually mathematically impose a restriction at this point, okay, at the point where it touches, saying that only this region is phase change, this is no phase change. Okay, so I have to mathematically, I call it as a penalty function. I'm going to show you that. Okay, so typically these are the key assumptions that we make. There is another important assumption that we make. I'll give you a small example. So if you take orange juice, okay, if you take a 1 liter of orange juice, if you take 1 liter of water, put them in another beaker or somewhere, what is the volume of the whole mixture? What would be the volume of the whole mixture? You take orange juice, 1 liter. I'm not talking about the mass. Mass will be conserved, that's fine. I'm talking about the volume. So you've got 1 liter of orange juice, 1 liter of water, mix them together. What is the total volume? Sorry? Why? Yeah, because it will occupy interstitial spaces between them, and it's a non-ideal mixture. Okay, it's a non-ideal mixture. For example, if you just have water and water, or water and something similar to water, then they will form 2 liters. Okay, but this one will not. And one of the assumptions here we make is that in case of water ethanol, ethanol is actually close to water, but it's a very there is a very big but there. The thing is, if you are at concentrations less than 60%, it will form a linear mixture. Okay, it will form a linear mixture. So that means that the net properties of the system are basically a linear. It can be based on your mass fraction. It will be just a simple arithmetic average. However, water ethanol is also, it's a bit of a mad system. Water ethanol, if you go beyond 90%, I think at 96%, it forms an azeotrope. Do you know what is an azeotrope? Azeotrope, so obviously if you have a binary mixture, each one has its different volatilities, and you can exploit them to separate them out. That's what we do in distillation. Okay, because each one boils at a different temperature. Based on the boiling, based on the temperature, you can segregate things. When you have an azeotropic mixture, it has a constant boiling point. You cannot split the mixtures. Okay, so but when it forms an azeotrope, your liquid properties are completely out. It's a more of a harmonic. I mean, you can't use this linear properties anymore. Okay, so the assumption here I'm making is that the water ethanol system is, I wouldn't say is amenable to a linear mixture. That means it is much lesser than the azeotropic point, but at the same time it's around, you can go up to approximately 70% of ethanol volume percent and all that. Okay, so clearly, so that is there. So you can have linear liquid properties. The other thing is obviously surface tension. Again, like yesterday, it's a function of temperature as well as concentration. Okay, so you will have variation of solutal as well as thermal. Okay, manganese. You will have the typical continuity equation here. Again, epsilon parameter is basically the height of the droplet. So if the height is h0 divided by the droplet r0 or d0, epsilon is a very small parameter. Okay, so it's a flattish droplet. So it's like a puddle, but not fully a puddle. Okay. Now, so and this is where the epsilon, this is where the lubrication parameter comes here. So what we do is when we put all these things together and employ all this, you will get these equations. The other thing I'm also assuming, it's a very bad assumption, but it is assuming, I know that it is incorrect, is that gravity does not play a role. So other thing I do is gravity does not play a role here. Okay, actually, if your vapor is more denser than the surrounding atmosphere, it will play a role. Okay, in case of ethanol water, I'm a bit okay, because Ethanol vapor is slightly less dense, so it's going to go away. So it's not going to shield the droplet. So basically gravity does not play a role, then that's why you get these equations in this fashion. You will have the usual concentration equation. This is the concentration equation in the liquid phase. Okay, and again, based on this, very similar to the lubrication problem we did yesterday, we'll have a normal stress balance. You'll have a evaporative flux, and both A and B have got different fluxes. Okay, we've got different fluxes. This also shows the variation of height as your evaporation happens. So this is also accounted for here. This is the kinematic boundary condition. And then we use the Hertz-Knudsen theory. So this is basically again a molecular kinetic based theory to actually prescribe our evaporation rate. So you got the JA and you got JB, and you can see that you got these exponents. So these are basically directly from van der Waals. So we don't want to worry too much about this. This is basically vapor pressure of A. This is the vapor pressure ratio. You've got the latent heat ratios and all that. Everything will come into picture. So you, again, like yesterday, it's a very, very rich problem. But here, the main issue is that you don't start with a flat interface. You're already having a curved interface with a possible contact line, and you have a penalty condition at this particular point, saying that this guy will not evaporate at all. All the evaporation and phase change and all the dynamics, everything is restricted to this region. Okay. So what we do is we again, like yesterday, we're going to do a quasi-steady linear stability analysis. So basically, we can freeze the base state in time as it evolves, and I'm going to show you why it doesn't work here. Okay. So basically, if you look at it, very similar to that, we will impose some sort of a perturbation amplitude. It could be fluctuation in temperatures, fluctuation in velocities, fluctuation in the local pressure, you name it. Okay. You can have any sort of a perturbation. A is a general perturbation. Okay. And you can see this over here. You can see that you've got a base state which is instantaneous. So there is no function of t here. So it's basically frozen in one time. You do a stability analysis, frozen the next time, do a stability, and so on and so forth. Okay. And then this is the disturbance that you impose. You've got growth rate in space, and you've got growth rate in time. This omega t is growth rate in time. K is the wave number. And again, both of these are complex quantities, so you'll find that you will have both spatial growth rate as well as temporal growth rate and so on. You do all this, and basically you substitute all of these equations back there. You get an eigenvalue problem, and again, as stability analysis will tell you, it won't give you answers. It will tell you whether your growth rate is positive or not. Okay, whether your growth rate is positive or not. What are the key criteria? What are the key physics that are playing a role? And that's about it. It doesn't give you any other answers. Again, if you look at the boundary conditions very carefully, so you got this drop. This is an exaggerated image. This is a boundary. This is basically your drop, and this is very close to the contact line. So you got a precursor layer. So the precursor layer, the thickness of the precursor layer again is dependent on the Hamaker constant. So basically, the droplet the minimum height of the droplet will always be the precursor layer. It won't go beyond that. Okay, that's the van der Waals restriction there. But if you calculate your precursor layer thickness, it is atomistic layer, so you're pretty close to the surface anyway. Okay, so you're not really worried about it. Most important thing you would do is you would check is within the precursor layer, your JA and JB are 0. So basically, you don't have any evaporation in the precursor layer. And the penalty function is put in this way. So basically, in the penalty function, you're restricted. Your height is always fixed at this point. You have no evaporation, so the height will not increase or decrease. Okay, and basically, the other assumption we make is you may have molecules. You may have some molecules depositing in the precursor layer, but essentially, what we are saying is there is no more volatile component in this precursor layer. So essentially, you're suppressing evaporation completely. Okay, that is also an assumption. Whether it's a good assumption or not, I don't know. But that is the one assumption that we could make, because if I don't make it, it's very difficult to solve the problem. Okay, so if you do all that, this is basically your omega. Okay, so what you have done is you've frozen your base states. For each of your base state, you will get omega versus k and some kind of a plot like this. Okay, you are talking about the most unstable mode, so basically the most unstable growth rate. So this is the maximum growth rate you can get. and what I'm plotting is the most unstable growth rate here. So I've frozen this in time for various concentrations and for various surface tension ratios. And what you'll find is you'll get the surface plot. It shows most importantly shows that if you increase your concentration of ethanol, you increase the growth rate. Okay, you increase the growth rate. Again, if you change the surface tension ratio between the fluids, you would also. So, in other words, if you increase your most volatile component concentration, you increase the growth rate. If you change the surface tension ratio, if you actually increase the surface tension ratio, you also increase the growth rate. Okay, so this is something which we get from quasi-steady stability analysis. But there is a problem. The problem is that I'm drawing a very ideal picture here. The real picture looks something like this. So if I look at omega versus k, I would get a plot which looks like this. So it hardly crosses the line k, and what it shows is that you may have a maximum point, but there are several other wave numbers, there are several other waves which can have a competing growth rate, okay, which can have a competing growth rate. And these particular points are just these maximum points. Now, if you have any system which has multiple growth rates, you've got, I mean, this guy is not very far from this one, this guy is not very far from this one. So these waves can actually compete with each other, okay? But your system is so small, the evaporation is so fast. So again, it made us think back into our assumptions. So the assumption we made for a quasi-steady stability analysis is you freeze the base state in time, which means that the rate of evaporation is so slow that you're able to freeze it and then slowly take all the things, go to the next state, again do the stability analysis and so. But these guys are so fast. Practically, they take hardly a fraction of a second to evaporate. Okay, so essentially, the question of QSSA, is it valid, that comes into picture. Okay, because the way it comes up is the way the anomaly comes up is you've got multiple modes which are highly active, and if you have multiple modes, you should see a lot of activity within the droplet. We don't see that. Okay, so you should see a lot of competing motion. It's like ocean waves. You should see number of waves competing with each other and so on and so forth. Okay, so what we have to do is we have to think about another strategy. Okay, so another takeaway message I would say from quasi-steady stability analysis is, if you have a more volatile system, you probably are not right in doing a quasi-steady stability analysis. Okay, you need to think about something else. Okay, with this I would like to just give a pause and ask you any questions if you have any questions, because so far I've just been doing a monologue. Any questions?
So maybe one or two things. Though mathematically I think it is not affecting much, but in practical scenarios, is it the more volatile one which will be forming the precursor film, or is it?
Very good question. So it is practically the more volatile one. But we have also seen some interferometry measurements. It's more of a mixture. This was for water and I think butanol. But again, if you have a more volatile system, I think it's predominantly that one.
But I think if there is some significant concentration difference between the contact line and the precursor film, can there be diffusion?
Yes, there would be. And so this is why we want to suppress it. We want to suppress that diffusion there. So we have restricted, saying that wo side kuch nahi hoga. Any further questions? Okay, so now we have a major problem here. The problem is we are able to do, mathematically we are able to do some stability analysis, but it's not really giving us answers which we can see practically, okay, which we can actually see through experiments. So we had to really question our assumptions completely, okay. So one thing what I can do is we can throw away the assumption of quasi-steady stability analysis, okay. So let's throw that away. So what does that mean? What does that actually mean? So when we do a quasi-steady stability analysis, if you go back you see that we are looking at an instantaneous base state. Okay, so instantaneous at time t equal to 0, your shape was like this. Your shape was like this, and I'm looking at this shape. At time t equal to 0.01, your shape was probably like that. I'm taking that. Okay, we are freezing that state in time. So essentially, there is no t over here. Okay, so other than that, what I'm going to do is, one way I can do it is a much more difficult one, but what I can do is we can make it as a dynamic base state. Okay, so essentially your disturbance travels with your base state. Okay, your disturbance is traveling with your base state. You will have a t term here, and you will also have a t term here. Okay, so that is it's a much more advanced technique, but it's a very convoluted technique actually. But again, what it will tell me is essentially with these systems where the base state is never going to change, and that is changing very rapidly, this is probably the only method I can use. Okay, other than DNS, but this is the only method I can use. So what we're going to do is we're going to do exactly that. So basically, we're going to say that it's very similar to quasi-steady analysis. You will again impose perturbations. You will again impose everything. Over here, you will impose a disturbance. You can see that A0, this is with respect to time. You got A1 with respect to time, and it is e to the power ik theta. In the previous one, you had a plus omega t. But here, because you've got t already embedded in it, I don't need to have plus omega t here. Okay, so this is how I'm going to impose the base state as well as the disturbance, and that creates a very intense problem. Okay, that creates a very, if I substitute everything back into the lubrication equations, it becomes a very very dynamic problem. So this is what I write. So I say that the perturbed stability equations now include a time dependent element to be solved along with the base state. Okay, so this particular time dependent element is not an easy thing to solve. Okay, it's not an easy thing to solve because that's also a part of the problem. And basically what we do is we take all the force equations, we integrate over space and time, and then what you will get is some sort of an integral which looks like this. It's a weak integral, but essentially what we then do is for any kind of variable, whether it is the height of the interface, pressure, any sort of function f, g, or this is temperature, this is flux, this is concentration, etc. For any of these parameters, we will see how it changes with time. We'll take a limit at infinite time, and we calculate the growth rate. Okay, so we calculate the growth rate. So basically, the growth rate of the perturbation is calculated in that way. So you need to have, number one, h as a function of t. You need to have h as a function of t, x as a function, there is concentration as a function of t, temperature as a function of t, and so on and so forth. So it becomes a very intense problem here. Okay, but then once you do that, you will be able to calculate the growth rates because you know how each parameter changes with time, alongside how your interface changes with time. Okay, so these are some of the results. So one way is, there's another problem. How do you put these results? Because if you have different droplets have got different evaporation times. Okay, so when I say t equal to 0, that is initial, that's constant for everyone. When I say t equal to 1, it may mean completely different things for different mixtures. For one mixture, you may hardly have any droplet left. For other mixture, there's almost fully droplet left. So what we do is we look at the percentage mass loss. So because we have calculated h with respect to t, we can also h with respect to t, we know the amount of mass left with respect to t. So when the mass left is about 90% of the original mass, we'll do the stability analysis. We take the growth rates. So if you look at this growth rate, this has to be done a bit slowly. So if you look at this growth rate, you've got these 3 dots here. The square one is at lower concentration. So all of these are with respect to concentration. So let us just track at low concentration. So at low concentration, you will have a plot which looks, and this is omega, this is growth rate with respect to a wave number. You will have a plot which looks like this, okay, and it crosses 0 somewhere here. Okay, this is at low concentration. So this is how the growth rate is at low concentration. So the most active mode has a wavelength. The most active mode has a wavelength has a wave number of approximately 1, so the wavelength is about 2 pi by 1, something like that, okay. The wavelength is about this, okay. Now, if I look at 50%, 50% is the circle, you can see how it has changed. So this is going to be a dotted line. Okay, so 50%, it's actually, it crossed the line a bit earlier, okay, it crossed the line. So you can see that the zone of stability has reduced here. It's only in the positive range up to a small extent. But then your most unstable, the most unstable mode is very much similar. So these guys are probably almost of the same height. If you look at 75%, this is far more interesting. So you can see that this goes like that. It goes like that. It's still not crossed the 0 line, and somewhere here it has crossed the 0 line. Okay, so you can clearly see that concentration has a completely non-monotonic effect. Okay, you can't just say 50% mesa hua to 75% mesa. No, nothing. We can't say anything like that. However, let us just look at later stage. So this is where you've got 40% of mass which is lost. So 60% of the droplet is remaining. Okay, and the thing is, one of the beauty of these methods is if you, what we assume is when 40% of the mass has lost, you have lost more of the more volatile component. You've got more of the more volatile component. But the moment all of the more volatile component evaporates, you won't get any results. Everything becomes 0. Okay, so essentially we are just tracking when the droplet is still a binary mixture. So if you look at this carefully, you will see that 25% it looks something like this. 50% it's flat. Okay, 75% is further flat. Okay, so here at 40% mass loss, you can see that the cutoff wave number, the cutoff where it becomes neutrally stable, has increased, has constantly increased. So one thing you can say is that when you are at lower concentrations, you will have very active, you will have very quick development of these spokes, very quick development of these spokes, but these spokes immediately die. Okay, so but reach the stability sooner. Okay, these spokes will immediately die. If you increase the concentration up to say 75% ethanol, you will find a lot more spokes. They're slower and they remain in time for a long period of time. Okay, so you can imagine if you're developing a kind of a pattern, it's probably best to have a high concentration alcohol mixture. Okay, it's probably best to have that. So you can see that you'll have more number of modes which are active, more number of modes which are competing with each other, and so on and so forth. Okay. Now, if you increase your, again, there is another thing which are there. If you increase the concentration, you find more number of modes, but at the same time, hardly anything approaches 0. Okay, hardly anything approaches 0, especially at middle stages of your droplet. Okay, so if I plot the cutoff wave number, so the cutoff wave number is basically these points here with respect to mass loss. This is the amount of mass loss. In a way, this is time itself. So at 0%, you start from this point, you will see that the cutoff wave number keeps increasing as you increase your concentration. Okay, so that means that you've got more and more active number of modes which are there when you have a high concentration of ethanol. That reduces if you decrease ethanol and so on and so forth. Okay, if you decrease the concentration. So if this is a very important statement because this can help you design your systems accordingly. Okay. Now, if you look at these experiments, this will keep playing. If you look at the experiments, so we wanted to compare these results with experiments. So what we were doing is, what Katie was doing is, this is 25% ethanol. You can see how fast it is. Okay, it just number one, it's low concentration, so it immediately starts evaporating, and it forms these spokes. It goes into the nonlinear mode very quickly. Okay, and you have certain number of spokes here. Again, 50%, you will see that the number of spokes is much higher. Okay, it's a far slower system, but it's a number of spokes is much higher. But then you have a lot of merging happening. If you look at it carefully, you'll see that there's a lot of merging happening, and you'll see a kind of a rim which is developed. With 75% ethanol, we actually don't know the number of spokes that is developed because it's very difficult to see. Okay, but the stability analysis shows that you've got a very high number of spokes. Okay, so you have a huge number of spokes. Again, you will have the system very quickly evolves into a nonlinear state, and resulting in a kind of a rim and this spokes fashion over there. Okay, so this is basically, I think this was a copper substrate, ethanol water mixture, 70 degrees Celsius, and it was probably the humidity was 60%. This was in Kyushu. So all these experiments were done in Kyushu. Okay, so the quick thing we want to check was how does it compare with our stability analysis? Okay, so when we plotted the wave number, it was giving the number of waves. Okay, number of waves, inverse of the number of waves is the wavelength. Okay, so here if you look at so at early stages, what Katie did was she looked at she counted by hand the number of spokes as things evolved. So you can see that the average number of spokes was around 16 at the early stage. But the thing is, this happened so fast that it was very difficult to pick up a proper image of the whole system. If you increase your concentration, you'll see that the number of spokes has increased. This is again the number of dots she was able to count. But again, obviously it's not correct. It might be more than that, but we don't know. Okay, okay. So basically we can say that at a lower ethanol concentration, you've got a far bigger spread. At higher concentration, you don't have much of a spread. You do have spread, you don't have much of a spread. In fact, in our previous paper, we calculated the extent of spread. You can have a look at it. And the thing is, the spreading is also pretty chaotic. I mean, it's very difficult to see where the spokes merge. You know that they merge, but it's very difficult to actually see it properly. Okay, and basically, you can see that these rims that are developed here, as the spokes develop, is because of a contact line instability. So that is a different, the mechanism over there leading to this rim is slightly different. It is a combination of Rayleigh-Taylor and everything else, but the origin of these spokes is a Solutyl-Marangoni instability. Okay, so you can see that, and in some cases, in some systems, I think water butanol, these guys also start rotating. Okay, so it's a very funny thing. So it's even more. So you have a kind of an azimuthal current which is set up. Okay, so we try to control this as much as possible with water ethanol. And even these experiments are very difficult because you need to have a flat droplet. So this is only for cases where the droplet begins with a contact angle of less than 30 degrees or 30 degrees. Okay, so managing that itself was difficult. But then once we were able to do, we could see these spokes that are developed. Okay, so spreading is more controlled. The spreading is more controlled and even with more instabilities. So basically what we have done today is basically look at two types of instability, stability analysis. One is a quasi-steady state stability analysis. So quasi-steady state stability, great for films. We have done it yesterday. It is absolutely fine. But when you have a droplet which is of a much smaller mass, it's not appropriate at all. You need to have, because it's a fast evaporating system and immediately goes in dry out, you need to make sure that you have a better system. So transient growth analysis, or where everything is a dynamic system, gives you a more appropriate picture of a dynamic instability. Very clearly, if you increase the concentration of the more volatile component, you destabilize the system furthermore. Okay, so and basically, and the reason why it is happening is because the Solutyl-Marangoni stress is the strongest destabilizer. Okay, yeah, and basically this also agrees with the experiment, so this is fine. So with this, I would like to stop the first part of the lecture. So we have done two stability analysis. So again, stability analysis will not give you an answer. It tells you whether your system is stable or unstable. Okay, but it's a very powerful tool. The other important thing is you can only use that tool with the assumptions that you have made. Okay, if you want to go beyond the assumptions, if you want to understand the later stage, there is only one good way of doing it. That is direct numerical simulations, which we're going to do tomorrow. Okay, so direct numerical simulations will help us understand the nonlinear growth of these instabilities and see how your final stage of the design of your experiments could be, or your system could be. So anyway, with this I would like to stop. If you have any questions, let me know. Any questions?
At higher concentration, spread is less.
Yeah.
Is is it the reason that rate of evaporation is high?
Yes, the rate of evaporation is very high. So the lifetime of the droplet is much lower.
These instabilities, which kind of Rayleigh Taylor effect, which type of
So the spokes are because of thermocapillary instabilities, but in here it is more of solutocapillary instability. It's concentration gradients. It's the concentration gradients on the surface, on the interface, so affecting the surface. That is the driver for these instabilities, predominant. That is the first driver. And then when everything else, when most of it has evaporated, it forms a rim. That could be other things. That could be a Rayleigh plateau, whatever it is. Yeah.
liquid interface or some kind of droplet splitting, the phenomena where the evaporation is not there, then the stability will work on this concentration.
So you mean segregation of components? No. Okay. So people, so I think Detlef group does Uzo droplet. Okay, but it's a highly ternary system, and obviously they have done some numerical simulations, but theoretical understanding is still not there. So what happens is you can have, if you have a ternary system. So Uzo is this liquor which Turkish drink, and if you mix it with water, it forms a very cloudy system. So then that's because you've got a Oswald ripening effect, and that's what you will see with temperature at some zones. So I think you have much more complex dynamics there. So it's still, yeah. Yeah.
So, in between early and later stages, can there be the difference in instability patterns because of difference in concentration of the ethanol at the contact line?
Yes.
Early stage it will be extremely high.
Extremely high, yes. Absolutely. And in fact, that also governs the growth rate of the instability, sorry, the wave number of the instability, the number of modes. That's the reason why you've got more spokes in case of a 75% ethanol system and all that, yeah. Yes?
So is this theory valid only for the mixtures or valid for the solutions?
This is valid for mainly binary mixtures, not ternary. So this is fixed for air.
Solutions like some people make the non-equivalent fluid by xanthan and DI.
Okay, so these are particulates. Okay, so basically colloidal systems, you mean? So, so we have done some work with salts. Okay, over there the nature of instability is quite different. You will have a solutal instability, but that's because of the salt. And salt also has this property of crystallization. So there are slightly different physics happening there. Viscosity does play a role. In this system, as I explained previously, water and ethanol are very close to each other. But then if you have other systems where viscosity, there's a big difference between the viscosity, yes, it plays a huge role. So this approximation is valid as long as you can do this, as long as you can still have so this is your total viscosity. As long as this mixture rule is valid for that system, this analysis is valid. If this mixture rule is not valid, you would have to change the mixture rule and rederive the equations of it. Any further questions? Yeah. Yes, partly why I'm neglecting gravity is because the height is smaller. The most important reason why I'm neglecting gravity is the vapor formed by ethanol is typically lighter than the atmosphere, so it goes up. Okay, it's not going to cover the drop. But if you have a heavier vapor, it's going to shield the droplet. It's going to drop on, and it will affect the evaporation pattern then. So at that time, I would have to consider gravity. Yeah.
So suppose we are artificially increasing the value of the voltage. 9.81 we are increasing much higher.
Yeah.
So will that affect the interface? Or
Yes, it does. It does. In fact, so when we set up experiments for ESA, that is one of the crucial things we look at. What is the range of gravity that we can allow, or that we can do for the experiment? So that is a crucial thing. So we look at the change of capillary length. We look at we ignore the effect of capillary. We say that gravity is valid all the time, but at some, obviously for very thin films it may not be as important, but we check that at what g is it not very important. Yeah.
in general, like for gravity, it is decreasing the apparent contact energy.
Yes. So one way where we look at is if you took a pendant droplet rather than a sessile droplet, you take a pendant droplet. If you evaporate this pendant droplet, if your vapor is heavier than the surroundings, you'll have a vapor stream which goes down. But then if it is not, it's going to just occupy there. So that's why if you have a pendant droplet, it evaporates much slower than a sessile droplet. Good. So I think I've done the first bit of my lecture. So
I think we can take 10 to 15 minutes break and
yeah, we can then start again. Yeah.